Chapter 14, Section 3, Behavior of Gases. So, the main idea for this section is that gases respond to changes in pressure, temperature, and volume in predictable ways. So, the real-world reading link: if you've ever climbed high up on a mountain, you might have had the experience of panting as it becomes more difficult to breathe. Modern jet airplanes fly much higher at altitudes where breathing is close to impossible. The cabins of these jets must be specially pressurized for people on board. In order to do this effectively, an understanding of the behavior of gases is necessary. So Boyle's law, volume and pressure. Have you ever seen a weather balloon like the one shown in figure 19? So this is a weather balloon. It's just a large balloon filled with helium that they attach equipment to. So weather balloons carry sensing instruments to very high altitudes to detect weather information. A weather balloon is inflated near Earth's surface with a low-density gas, usually helium. Recall that a gas completely fills its container. The balloon remains inflated because of collisions that the gas particles inside the balloon have with the balloon itself. In other words, these collisions between gas particles and the container wall cause the gas to exert pressure on the container. As the balloon rises, the atmospheric pressure outside the balloon decreases, and this decrease in pressure allows the balloon to expand, eventually reaching a volume between 30 and 200 times its original size. Boyle's law describes the relationship between the gas pressure and volume that explains the behavior of weather balloons. So volume and pressure. Because a balloon is flexible, its volume can change. In the case of the weather balloon, the volume increases as the external pressure decreases. So the volume increases as the external pressure decreases. The volume of the gas inside the weather balloon continues to increase until the balloon can no longer contain it. At this point, the balloon ruptures and the sensing instruments it was carrying fall to the ground. From the weather balloon, we know what happens to volume when you decrease pressure. What happens to the pressure from a gas if you decrease its volume? For example, by decreasing the size of the container in which the gas is held. So think about the kinetic theory of matter. The pressure from a gas depends on how often its particles strike the walls of the container. If you squeeze gas into a smaller space, its particles will strike the walls more often, causing increased pressure. The opposite is also true. So if you give the particles that make up the gas more space, increasing the volume, they will hit the walls less often and the pressure from the gas will be reduced. So Robert Boyle, 1627 to 1691, a British scientist, described this property of gases. According to Boyle's law, if you decrease the volume of a container of a gas and hold the temperature constant, the pressure from the gas will increase. An increase in the volume of the container causes the pressure to drop if the temperature remains constant. So figure 20 shows the relationship as the volume of a gas is decreased from 10 liters to 5 liters to 2.5 liters. Note the points on the graph that correspond to each of these volumes. So if we notice here in the diagram, we have our gas particles inside this container, and we are basically pushing this piston down. As we push this piston down, these gas particles, still moving at the same speed because it's still the same temperature, they have to move in smaller and smaller spaces. So the volume decreases, the pressure increases. So we kind of see that here. We have volume increasing this way, but actually we are decreasing the volume. So we start off at 10, we decrease it to 5, we decrease it to 2.5. As we do that, the pressure increases. So an equation for Boyle's law. Boyle's law can be expressed with a mathematical equation. When the temperature of a gas is constant, then the product of the pressure and the volume of the gas does not change. So Boyle's law equation, so the initial pressure times the initial volume equals the final pressure and the final volume, or PI VI equals PF VF. The product of the initial pressure and volume, designated with the subscript I, is equal to the product of the final pressure and volume, designated with the subscript F for final. You can use this equation to find one unknown value when you have the other three. So you have to have three of these values, but then you use some algebra and you solve for the missing variable. The equation will work with any units for either volume or pressure as long as you use the same units for the same pressure units for PI and PF and the same volume units for VI and VF. So units don't really matter here. As long as you're using the same units on both sides, you should be okay. So example problems, we'll get to those later. That's a separate assignment. Okay, Charles' law, temperature and volume. If you've watched a hot air balloon being inflated, you know that gases expand when they are heated. So gases expand when they are heated. Jacques Charles, 1746 to 1823, a French scientist, also noticed this. According to Charles' law, the volume of a gas increases with increasing temperature as long as the pressure on the gas does not change. As with Boyle's law, the reverse is also true. The volume of a gas shrinks with decreasing temperature, as shown in Figure 21. So if we go up here to Figure 21, we kind of see we have gas A, gas B, gas C. We have temperature in Kelvin increasing this way. We have volume increasing this way. So if we increase our temperature, then we increase the volume. So if we heat it, so if we're increasing the temperature, so we're increasing the temperature here, we also increase the volume. The opposite is also true. If we decrease the temperature, here, then we also decrease the volume. The kinetic theory and Charles' law. Charles' law can be explained using the kinetic theory of matter. As a gas is heated, the particles that make up that gas move faster and faster. Because the particles that make up the gas move faster, they strike the walls of their container more often and with more force. So if the hot air balloon, or in the hot air balloon, the walls have room to expand. So instead of increasing pressure, the volume increases. So an equation for Charles' law. So like Boyle's law, Charles' law can be expressed mathematically. When the pressure on a gas is constant, so the pressure has to remain constant here, then the ratio of the volume to the absolute temperature does not change. The absolute temperature is the temperature measured in kelvins. You have to convert this to kelvins. You cannot do this in Celsius. So unlike Boyle's law didn't matter what the units were necessarily as long as you use the same units on both sides. Charles' law, you have to have the temperature in Kelvin. And remember, to convert to Kelvin, we take our temperature in Celsius and add 273. Okay. So Charles' law equation. So the initial volume divided by the initial temperature in Kelvin is equal to the final volume divided by the final temperature in Kelvin. And again, if you know any three of these, you can figure out the fourth one. So this shows that the ratio of the initial volume to the initial temperature is equal to the ratio of the final volume to the final temperature. Remember that temperature must be in kelvins. So remember that when you're doing the example problems later.